don't know the first thing about who you are. My heart is waiting, taking.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we can actually do a problem involving the equation that we looked at before. And in this problem, it says calculate the frequency of light emitted by a hydrogen atom when an electron makes a transition from the fourth to the second principal quantum level. So what this means is if you have these energy levels, or let's say this is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. You want to calculate the frequency of light that's emitted by a hydrogen atom when the electron makes a transition from the fourth to the second, and in this relaxation, it basically emits a photon. So the first thing we need to write out is the equation that I showed you from before, En equals negative HR over n squared. So in this case, we're looking at the fourth energy level. And so for this, it becomes negative 1/16, since it's n equals 4, 4 squared is 16, HR. So this is 1 over 16, 6.626 times 10 to the power of negative 34 joules second. And the Rydberg constant I mentioned before is 3.29 times 10 to the power of 15 inverse second. The seconds cancel out, and we end up with a value in joules, and we get negative 1.36 times 10 to the power of negative 19 joules. And now using the same exact equation, we can calculate the energy value at E2, since it's going from n equals 4 to n equals 2. And doing that, we get 1/4 HR, and that value is negative 5.45 times 10 to the power of negative 19 joules. So the change in energy for the electron we can now calculate is delta E is E final minus E initial, which is E2 minus E4, right? Since this is the final quantum level and this is the initial one. And so we just plug the values in as negative 5.45 times 10 to the power of negative 19 joules minus negative 1.36 times 10 to the power of negative 19 joules. And we end up with a value of negative 4.09 times 10 to the power of negative 19 joules. Okay, so this is the delta E. So the minus sign exists because the electron's energy has decreased when it's going from n equals 4 to n equals 2, and the energy is released as electromagnetic radiation, as you can see right here. And now we can use E equals h nu to calculate the frequency of this light that's being emitted. And so we've seen this equation before too. Nu is E over h, which is just a rearrangement from E equals h nu. And we get 4.09 times 10 to the power of negative 19 joules over 6.626 times 10 to the power of negative 34 joule second. So basically we ignore this negative sign when doing this part of the calculation because all this is telling us here is that the electron's energy decreased. Okay, so we end up with 6.17 times 10 to the power of 14 invert second, which is 6.17 times 10 to the power of 14 hertz, depending on which unit you want to end up with. Okay, so it seems complicated, but it's actually really straightforward, where if you're asked to calculate the frequency or the wavelength of a light that's emitted when you make a transition change from n equals something to n equals a lower energy value, you first have to figure out what that energy is for that certain wavelength, then use those values to find delta E, and then use that to finally calculate for frequency, for wavelength, etc. So I hope this makes sense.